All right. Hello, I am Sarah. I'm from the University of Virginia. I'm going into my 5th year for my PhD. My advisor is Dr. James Burns. And today I'm going to be talking about stress corrosion cracking for the application of nuclear waste canisters within the United States. This research is in collaboration with San Diego National Labs, as well as Sensitivities Corporation, and it's also funded by United States Nuclear Regulatory Commission and the Department of Energy. So nuclear waste is a pretty common topic, but we'll just quickly go through the background. For storage in the United States, there's 2 different ways. There's vertical dry cask storage, and there's also horizontal cask storage. And then when it comes to these cask storage systems, it is stainless steel canisters, specifically welded austenitic stainless steels that are placed into a concrete overpack. And then there's vents on the top and bottom and air space in between that stainless steel and that concrete that allows ventilation so that canister for the stainless steel is staying cooled. But this also then allows the deposition of outside constituents and particles and salts to be formed on that stainless steel canister surface. And so nuclear waste within the United States is stored across most of the states. There's a lot of climate changes between all of these canister sites, and there's also going to be a lot of changes in between what is being deposited on these canisters. And so we needed to look into this a bit more. These canisters are going to be susceptible to stress corrosion cracking. Specifically, one, we get this deliquescence of the deposition, the salt deposits onto this canister. And then along with that, the initial canisters were made in the 80s, and they thought it was supposed to be the short-term solution. It is now the long-term solution. So they were not manufactured well. And so there is a considerable amount of residual stress around these welds. And along with this, then specifically 304L and 316L were the stainless steels that were used. And we do know from previous literature that these are susceptible to stress corrosion cracking. And so our main goal for our part of this task was to help create an engineering model that's going to help rank the risk of these sites, which ones need to be of more concern starting off, and then also try to determine which factors we actually care about, whether it's temperature, whether it's chloride, what's actually going to affect that crack growth. I don't know why this is washing it out so much. I swear it looks better on my laptop. So this is going to be really unfortunate through the whole thing. Oh well. This was the model. Basically, we used a bunch of different things. I'm not really going to focus on this for the talk, but the overall goal was you input the stress, you input geometry, flaw sizes from either inspection results, which we've been doing with the Department of Energy, or just maximum pit size models that come from Dr. Kelly's group at UVA. This will then create the driving force. We use dAdt versus K crack growth kinetics. Combined with that driving force, you can get a lifetime prediction, was kind of the goal. And so my part of that task was to start developing a database for these crack growth kinetics with SEC. And specifically, we were looking at individual constituents and trying to find the boundaries of the worst and best case scenario, as we're the first attempt to do this within the US. And so we are just starting to try to figure out what actually matters, what's the worst case scenario, what's the best case. Our testing. So we do real-time crack extension, DCPD specifically, and this allows us to measure the crack in situ and then allow for K testing. And so we do K-rise testing at a dKdt of 0.33 MPa square root meter per hour. And then also along with this project, I created a high temperature environmental cell. So this allows us to do either full immersion or atmospheric conditions at anywhere from 23 C to 100 degrees C. And so that's kind of the overview. This is very nice. This is just the overall kind of data that we've started to collect. We've done temperature dependence, microstructure dependence, which is going to be our 304L cold rolled versus our 304L annealed. And then we also have done composition dependence, so 316 versus 304 annealed, as well as orientation dependence. The plate that we have of 304L annealed has ferrite stringers in it. This was provided to us by Sandia, and so we wanted to see the effect of if we were cracking along the ferrite stringers or cracking through them for orientation. But all of these were done in full immersion environments, which isn't really conducive to what the environment of that canister is going to be. But it did help us to determine kind of what the extremes were for that. And so these were all done in full immersion, but what is actually a relevant canister environment? Sandia has done quite a considerable amount of work to help determine this environment that's going to be on the canister. They've done predictive modeling to determine canister surface temperature over 300 years as that nuclear waste decomposes. Then that was able to predict the relative humidity. And with this increasing relative humidity on that canister surface, we will start to deliquesce these particles that we are seeing on that canister surface. And with this deliquescence of these particles on the surface, we are then going to start getting a thin film electrolyte that is going to be formed on that canister surface. So what would be unique compared to a full immersion testing about the electrolyte formed by salt deliquescence? The main thing is that it's going to be dependent on fluctuating temperature as well as relative humidity of that canister surface. And so eventually with time, we're going to start getting where that relative humidity is going to fluctuate quite a lot around that deliquescence of magnesium chloride, which is something that is found on those canisters. And when it comes to these fluctuations and just atmospheric conditions and deliquescence in general, it affects two main things. One is going to be that electrolyte composition. It's going to change the concentration of the solution on that canister surface, as well as electrolyte geometry, so that water layer thickness, and that's what we're going to be quickly looking at today. So why would electrolyte geometry impact stress corrosion cracking? That's fine. So when it comes to the electrolyte geometry, changing the electrolyte geometry could either increase or decrease that cathodic current. And so this cathodic current will then affect our overall crack growth rate. So what might cause that that cathodic current to decrease and then decrease our EAC susceptibility between atmospheric and full immersion? One of the things is that water layer thickness from other material and conditions has been shown to be directly correlated to the available cathodic current as well as the size of the cathodic current. So decreasing that water layer thickness with going from full immersion to a misting environment could limit the available cathodic current. And then this will cause a decrease in our EAC if we decrease that cathodic current with that decreasing water layer thickness within atmospheric environments. Why might the electrolyte geometry increase EAC susceptibility? So recall that the cathodic reaction at that bulk surface is what supports the ionic dissolution. So that cathodic reaction is the OOR, the oxygen reduction reaction, and this is limited by the diffusion of oxygen to the surface, just due to the fact that oxygen is not very soluble in water. And so when we, one of the only ways to vary that diffusion limited cathodic current is, one of the only ways to change that cathodic current density is going to be by changing that diffusion distance of oxygen and therefore the water layer thickness. And so in full immersion, that diffusion distance is controlled by natural convection. But if we go to misting, it then is going to be just controlled by how thin the electrolyte is. And thus that cathodic current is going to be higher because of more oxygen supply, and thus we'll get more. There's materials that have shown both. I'm talking too much, so we're gonna get moving. The overall project motivation was that there's a thin film that's probably going to be on the canisters, but then scientifically, we did want to see what the roles of both cathodic limitation and that oxygen availability are going to do to the EAC seen in 304, and which one will determine crack growth at 23 and 55C. So this is kind of an overview of the testing. It's the same thing that we talked about, but one of them was going to be full immersion, where we're continuously pumping full immersion solution through the cell, and the other one was a continuous misting spray. First, we did a full immersion cathode size availability test just to see what would happen if we limited the cathode size physically. We used a chromate lacquer to do this. And so one of them was a large cathode size where the DCPD wires were welded. And then on the small one had 1 millimeter of crack growth, or 1 millimeter of free surface around that crack path. So we found that limiting that cathode size in full immersion conditions did decrease our SEC susceptibility, but one of the main things to take away is that this impact of the cathode size was a lot more prominent within our 55C testing conditions compared to the 23C in full immersion. So then we can move on to the misting versus the full immersion testing that we've done. And we originally did it at 23C with that large cathode sample. So only that front part was painted. The rest of it was available for testing. And the cathode size is then only going to be limited by that electrolyte or like the misting conditions. We did actually find, though, at 23C that atmospheric conditions were more susceptible than our full immersion. And so this would indicate that that oxygen availability is what is going to be causing that increase in stress corrosion cracking. But we did want to just confirm that this was right. So we also did it with the small cathode samples where we physically painted them. And so we did a full immersion small cathode and an atmospheric small cathode, and we still saw that that misting was more susceptible than that full immersion. And so this would indicate that oxygen availability is what is going to be playing a more crucial role for SEC susceptibility at room temperature, or 23C, than that cathode size limitation. But 23C is not really, it's going to be a while until the canister hits 23C. It's going to hit 55C first. So what happens at 55C? Well, we did a test and we actually found that this 55C, so this is crack growth rate versus stress intensity. We found that that full immersion is actually more susceptible than that misting conditions, which is the exact opposite of what we saw at room temperature. So why could this possibly occur? If we go back to that full immersion cathode stuff that we talked about, where we just painted the samples, we could see that at that large cathode availability, 55C, which is this red one, because I don't think you can see it. 55C is this red, the blue is 23C, and same for these. At the full immersion large cathode, the 55C is about 6 times more susceptible or faster in crack growth rate than that 23C. But then if we limited both of their cathode sizes for that small cathode, they're pretty similar. And you would expect 55C to be more susceptible than 23C. So this kind of tells us that at 55C, it is pretty heavily dependent on that cathode size. And so this kind of makes sense for why at 23C, we're seeing more of the oxygen availability is controlling our stress corrosion cracking, but then at 55C, it switches to being more cathode size availability dependent. And I think that's exactly what I just said. So, one of the notes, this research is still ongoing because I'm still doing my PhD. One of the things we don't understand is why only really the K1 SEC has been affected. So that like stress corrosion cracking initiation, we don't really understand why stage 2 crack growth rates aren't super affected when it comes to atmospheric versus misting conditions. We're hoping to investigate this with future work. If anyone has ideas, I'm open to suggestions. And with that, that's conclusions. I'm going to leave them up because I probably went pretty long.